Hi everyone. So today's topic is data visualization. For data analysis, visualizing your data is very important because that's how you show your data and how you can make the data or results convincing to other people. So there are 3 rules of data analysis. It's simple but important. Okay, when you are analyzing data, you have to make a picture of data, make a picture, and make a picture. This is so important. So textbook is repeating it. Make a picture, make a picture, make a picture. Always make a picture. That's important. But why we make a picture? To think, show, and tell. And also, we want to make it cool. There are examples here. This is a website that has really cool data visualization. Actually, when I have time, I really enjoy the visiting these kind of data visualization web pages, and I'm getting many ideas from this. I actually want to go there with you. Let's see. So this is a web page, data-driven documents, and that's about JavaScript or something like that. There are many cool pictures, cool visualization methods, like when you are visualizing the network structure, you can do this, use this kind of circles plot, edge bundling plot. And for example, what else? This is another hierarchical clustering plot. Cool. You can show many things using these. So this is another interactive plot, I guess, like Obama versus Romney and stuff for each occasions. Yeah, this is really cool. So this person who made this, he I think works for New York Times, and yeah, super cool. This is another network plot, maybe 3-dimensional. Yeah, so you can get many ideas from this kind of plots, and you can use this for your paper, for example. Yeah, super cool. And yeah, this we call it hyperplot. Yeah, I kind of wanted to use this for brain networks. Yeah, it would be really cool. Anyway, so why visualization matters? So we are lazy and don't like to read. When I see the papers, I usually see the figures first because I'm lazy. And some information isn't easy to describe verbally. So it's really hard because if the data are large, the information without visualization, it's really hard to convey the gist of the data. And statistical summaries can be misleading. There are examples. The Anscombe's quartet. This is an example. So each plot has the same regression line and also same correlation, I think. So what the correlation is, we are going to learn that in later lectures. So correlation, that's the correlation tells us about the relationship between 2 variables. So these 4 variables, 4 plots, has the same summary statistics, correlation, and also the regression line, regression coefficients. Usually we say that as a regression slope. But as you can see, from these plots, the distribution of the dots are totally different across these 4 different plots, different cases. Okay, so statistical summaries can be misleading. And aesthetically pleasing visuals are engaging. So you can get people's attention to your data using the beautiful plots. So there are some textbooks example data. This is a frequency and contingency table of ticket class and survival for Titanic passengers. You know the Titanic, right? There were a tragic accident and many people died. So this is frequency table for the class. So first class, second class, third class, and crew members. And this is contingency table. So we are adding, this table has one more information about survival, so alive versus dead. And you can see that first class, I mean, there are more alive people than dead people, and so on. So let's say you wanted to plot this, and then you wanted to use this shape to express your data. But what's wrong with this plot? So there is an area principle. The area occupied by a part of the graph should correspond to the magnitude of the value it represents. But if you use this kind of 2D, the shape, the area will be squared, okay? So even though the difference between, for example, first and third is around twice, but it actually looked like 4 times. This is a little better. So this is important to think about. So for this type of data, you usually use bar plots. Like the y-axis here shows frequency, and x-axis is classes, and first, second, and just simply showing the values in y-axis. This is same, but heights are different. You can use relative frequency, or you can use this type of pie chart. And there are some concepts that you need to know to move forward. So there is a marginal distribution. So because there are 2 types of variables, one is class, one is class and another is survival, we can get the sum of the each values, and this is marginal distribution of survival. So you can get the number of alive and dead. You can see this was tragic accident. A lot of people died. And this is marginal distribution of class. Okay, the sum of the classes. And this is conditional distribution. So satisfy a condition on another variable. So this is showing a live condition on classes. Okay. So this is conditional distribution. So we want to make a chart for conditional distributions. You can actually divide the total population into 2 classes, alive and dead, and then show the proportions of the classes. Or you can use 2 different bar plots. As you can see here, for alive people, you can see this trend, and for dead people you can see this trend. So in the first class there were more people alive than dead, but for crew people there were more dead people than alive. So you can also use this stacked bar plot. So when you are saying the 2 variables are independent, that means that when the distribution of one variable tells us nothing about the distribution of the other variable. So if the survival variable doesn't tell us about classes, or the class variable doesn't tell us about nothing about the survival, then they are independent. But here, as you can see, the class information tells us something about survival, right? Then they are not independent, they are dependent. So there is another really interesting phenomenon or interesting concept, that is Simpson's paradox. So let's say there were 2 pilots, Mo and Jill, and based on this data, who would you say is the better pilot? So Mo got so this is proportion of on-time flight. So 100 times out of 120, so total 30%. Mo got had a successfully flew, arrived the destination on time. But Jill had 78%, only 78%. And based on only on this data, I think we can say Mo is the better pilot. But if we see in detail, if we see the data for day and night, the interesting thing happened. Here, Jill got a success rate, the on-time flight success rate of 95% for day, and for night flight 75%, and for Mo 90% for day and 50% night. And there, I mean, for both flights, Jill was better, right? So this really because of the different difficulty. So night flight, there is low probability of getting the on-time flight. So that's why this is better. And here, Jill got much more night flight because Jill was better pilot. So now who is the better pilot? Jill, for sure. So what does this Simpson's paradox tell us? Don't average over things unfairly. So day and night flight, they have different levels of difficulty, and the different numbers in different categories for day and night. We need to see the actual numbers. So we need to be careful about this type of averaging. What can prevent us from making that mistakes? So visualization, data visualization kind of can protect us from making mistakes like that. So we want to see the raw data, and for quantitative data, a histogram is a good way to show the data. So this was the data that I showed you last lecture, that the data I got from the last year students, and this was a sleep hours last night, and this is a sleep hours average, and I actually used histogram in the previous lecture. So this is histogram. So there are other types of plots you can use for this type of data. So this is a histogram that I showed you. Here the data is about pulse rate, beats per minute. It's around 60, and number of women. And this is stem and leaf display and shows the numbers. So this is 56. There was a 56, and there was a woman who had a 60 and 64, 64, 64. So three people who had 64. Just to make it simple, just uses a line and then have the tens, the number for tens here, and then ones here. 60, 56, 60, 0, 4, 4, 4. That means there were three people who had 64 values, and 68, 8, 8, 8, 72, 2, 2, 2. So there were four people who had 72 and 76, four people who had 80, and two people who had 84, and so on. So you can see now the dot plots. So this is another data, winning time and number of races, and you can see the numbers. It's similar to histogram, but a little more detailed. And this is another dot plots. So there are many different types of data visualization to show these numbers. And we want to know the shapes of the distribution. So there are modes, different modes. This is unimodal. That means there is one bump. So the distribution has just one group, and there is there could be bimodal, that is like that, the two bumps, and uniform is just one. Okay, not the bell shape, but just uniform, same distribution, same probability across the numbers. And there could be multimodal, multiple bumps. Okay. And the important thing about shapes is that symmetric or not. So this is left skewed, not symmetric at all, right? And this is symmetric, the bell shape, that's really famous normal distribution, right? So symmetric, and this is right skewed. So you need to see the distribution of the values, and then and then decide which distribution, which shape this is. So modes and symmetric. When you understand the distribution, the shapes of the distribution, you want to provide some summary statistics, summary values for the distribution. And one important thing is the center. And the median and mean values are the common values, common center statistics. And the first one is median. Let's say you have the number of earthquakes. So this is frequency, and x-axis here is magnitude of the earthquakes. And the median splits the histogram into two halves of the equal area. So let's say there were 76 earthquakes, and the median should be the 88.5th value. Because it's an even number, there is no exact center location, so we divided that into by 2, and we are getting the average of the two values, 88th and 89th, and 88.5th just is the average between average of the two values. If there was odd number of earthquakes, you can get the exact center value. So 111th values among the 221 earthquakes in the sorted data. Just sorted from the smallest number, small number, to large number, and then you can get the center number. So if you get the center, you also want to show how the data spread, how spread the data are, and there could be many different values, but a simple thing is range. Range is max minus mean, so maximum value, the maximum value here, and minus the minimum value. And interquartile range is IQR is upper quartile minus lower quartile. That means 25th value minus 75th value. These values, so here, so here the pink area is 50%, and this is 25%, and this is 25%. And IQR is just get which values, this minus this, okay? So how spread the middle 50% are. So these values are used in Boxplots, and we can use those as a 5-number summaries. So I actually collected data from my smartwatch. That is my heart rate data for a week. That was a couple of years ago, July 10th to 14th. So let's say this is frequency and this is my heart rate. So I made box plot, and the box plot here, the line here, that is median. It's around 70, and then this is quartile, so 75%, and this is 25%, and this is gonna be 50% of the data. And usually there is a line outside of the box. This one is 1.5 times IQR. And I said this is IQR, right? And 1.5 IQR. So you are adding the 1.5 IQR from the Q3. So Q3 plus 1.5 IQR and Q1 minus 1.5 IQR. So that's the range. And outside of that range, we decided that as outliers. So plus signs are outliers here, and this is far outliers. So I don't know what happened in this time. My heart just raced. So here the median value was 69, and Q3 was 74. Q1 is 66, and max was 160, and mean was 49. So this is the 5-number summary. Okay, using this we can know how spread the data are, and the center and middle 50%, and so on, right? So it's really informative. But if your data has a symmetric distribution, we can use the mean value. This is really simple, just average. So let's say I have this data and this red line is a mean. But as you can see, this doesn't seem to be a center, right? Because there is an outlier. It really draws this into this direction. So it's a little bit skewed. So if I omit these values, it looks like more symmetric. And then the mean value here, this is the mean value after I remove these outliers, far outliers. And then this looks like more looks like center, right? Center. So mean works for symmetric distribution, but doesn't work really well for skewed data. Okay. Yeah, these are what I just said. And there is another value for spread of symmetric distribution, that is standard deviation. It's really commonly used in the field, in research. So this is variance. So variance is so y each values minus the mean value. So that is gonna be let's say I have the data a lot here, and let's say this is a mean, and I have the value here yi, and then this is y hat mean, and then just difference between these two, and square it because we don't want to minus values, because this should be about some distance value. So y minus y bar, and square it, and then sum it and divide that by n minus 1. Why n minus 1? I will teach you why we divide that by n minus 1 later lecture. It's related to a degree of freedom, but yeah, it's coming later. And this is variance, and if we square root of that variance, it becomes standard deviation. Standard deviation is square root of the variance. So we can actually calculate these. So for example, let's say original values are here, 14, 13, 20, 22, 18, 19, 13, and then mean is 17. And we can calculate deviations. Deviations is just this, yi minus y bar, and just by subtracting these values, original values, with 17, you can get deviations. And because we don't want minus values, we squared the deviations. So now 9, 16, 9, 25, 1, 4, 16. So add up the squared deviations, 9, 16, and then it will become 80. And now divide that by n minus 1. So total number of the data is 7. So divided by 6, and that becomes 13.33. And finally, take the square root, that is 3.65. Okay. So we learned about visualization, bar chart and pie chart, and Airy principle and contingency table. And we learned marginal distribution and Simpson's paradox. And we also histograms, stem leaf, dot plots and shapes, center. There was a unimodal, bimodal, multimodal, and uniform, and symmetrical or skewed, and center, median, and mean, and spread, range, IQR, various standard deviation, and box plots. Okay, so that's it for today. And in the class, we will, I think we will try to draw a box plot together. Okay, prepare the questions and ask them in the class. See you in the class. Bye.